Good afternoon. Hello, everybody. My name is Joe Innocente. I'm the Wall Systems Market Development Manager for Suprema. Really excited to be here today. This is a great opportunity to talk about a number of issues, a number of things, exciting things that are going on in the building industry today. The real thermal performance of wall assemblies, vitally important going forward. And we're equally excited because we've just recently launched, Suprema has launched what we call the Better Build Wall Assembly program. Exciting opportunity, a lot of great stuff going on, a lot of great ideas, innovative ideas that will really help the construction industry get to the next level. Energy efficiency in the building envelope. Vitally important at this stage in our economy, in our society, and in our environment. We're at a crossroads. How do we reduce greenhouse gas emissions? Number one thing that we can do is increase the efficiency of the building envelope, because buildings still account for 48% of all the energy used in Canada today. Where can we make the biggest impact in terms of greenhouse gas emissions? And it's in how we run, how we heat, and how we cool our buildings. It's interesting, if we go back in time, let's go back 22 years, 1993, really important year. Why? Because that was the introduction of air barriers in the National Building Code. And how have we done over the past 22 years? Not too bad, but not too good either. So we've had 22 years to work, to play, to figure out how to make the building envelope better. Have we done very well? Most of the gains that we've actually had with respect to energy efficiency between heating and cooling has come from our mechanical, our HVAC industry. The efficiency of those units has really ballooned, has really skyrocketed. Has the building envelope kept pace? Based on these numbers, no, not even close. And why is that important? Well, there's this really important date, 2032, that's been set by by the federal government as a date when all new buildings built by 2032 are going to be net zero or passive house quality buildings. That is only 12 years out. So what's the difference between what we're currently building today and where we have to be in 12 years? So if a current building, let's say an average 3,000 square foot home, small, it's simple, and annual energy usage, 40,000 kilowatts. Where do we have to be by 2032? Again, it's only 12 years away. 1993 was 22 years ago. What have we done in 22 years? Not much. Where do we have to be in 12 years? We have to be here. We have to conserve 60%. The energy usage is going to go from 40,000 kilowatts down to 10,000. That is a dramatic decrease in the amount of energy that we're expected to use. And how are we going to get there? That's asking a lot of an industry that really takes time to get going. You know, the construction industry is not the most dynamic, not the most nimble of industries out there. But what Suprema has done is we've developed a guide. And in that guide, what we've done is we've taken a rather complex issue, and that's building codes. Who here understands building codes? A handful. Do you really understand building code? They are written by a group of people who really don't want you to understand it. It's not the greatest bedtime reading, to say the least. But what we've tried to do at Suprema is we've tried to simplify it so that you can actually go into this guide, and it will spell out where you have to be in order to meet NECB 2015. We've simplified it, we've done the thermal analysis, and we've also done a number of real-world analysis to make sure that these guides are accurate. We're not going to spend too much time here because the guide is available today online. You can register, go to the Suprema website, and you will actually find it, and you can download the full copy. It's, in my opinion, a very well thought out and easy to read and easy to use guide. So the effective thermal performance of, yes, Suprema wall assemblies, but also all wall assemblies. So let's say that one thing that we're emphasizing here, materials play a huge and important part in getting to where we need to be by 2032. But just as important is that little component called labor. You can have the best materials in the world, but if you can't assemble those materials properly, or if the details are not important, or workmanship is, well, price is king, workmanship is secondary, we're never going to reach where we need to be. Are we going to be responsible world citizens? Are we going to do our part? Are we going to lead in this next green economy? Or are we going to just be the ones left behind? Let's start at home. Let's start building better today. Because we know, it's not rocket science, it's not news, it's been around for a long time. The use of an air barrier and continuous insulation are the most effective ways to eliminate thermal bridging and air leakage associated with traditional stud frame and cavity insulation. You can't have one without the other. You can't throw more insulation at the problem without considering the effects of that air barrier. They work hand in hand together. Product and workmanship. Like I said, these are assemblies we're talking about because they've been in the code since 1993. They've been around for a long time. There's a number of things that we qualify in terms of being an air barrier. Okay, and I'm sure you've all seen this. This has been around for a long time. It must prevent airflow. Continuous. That's a word that we like to throw around a lot. Continuity must be continuous. Really must be. That is very, very important. Durability. What do we mean by durability? Is it going to last until the facade goes up? And then we're going to forget about it? Or is it going to last for the life of that building? That 100 years, that 200 years. How long do we want our buildings to last for? Want to build them and then in 20 years knock them down again? Is that sustainability? Is that the green economy? Not even close. Transfer load, resist creep, flexibility. These are all things that building materials must conform to, especially our membranes. They're designed to be flexible. Buildings move. We tend to quote this number. This is air leakage. This is any product that has air leakage below 0.02 liters per second over 1 square meter, it's a mouthful, is considered an air barrier. But there are literally thousands of products that conform to that product characteristic. A single product cannot perform all 6 of these assemblies or all 6 of these requirements. Only an assembly can. There's not one individual product that you can put on a wall, stick it up, and it can conform to all 6 of these characteristics. So for air barrier materials, there are standards. I love these standards. It's just licensed to print money by certain people. So we have ASTM, we have CAN, ULC. Very important because they must conform to the code, and the code requires them to meet certain standards. The standard that is important to us in the industry. Yes, product standards, it's the assembly standards. An ASTM E2357, which is our American standard from south of the border, or our CAN ULC S742, which is a Canadian standard, developed in Canada for Canadian buildings and Canadian products. The whole thing behind wall assembly standards, hopefully, is that there's a component in there that we refer to as the assembly, the labor part. Materials do not put themselves together by themselves. They need people. I can't emphasize how important having that labor component. Again, you can have the best products in the world. If they're not put together properly, they will fail. Your building will fail. We will not get to where we need to be. Okay, I'm not picking on this one particular product. I just saw this building and I couldn't believe. Who's taking responsibility for this application? Is the designer? Is it the building official? Is it the general contractor, the builder, the owner? Someone has to take responsibility. Okay? You have a product here, it's not doing anything. And you would think, this next picture, what are they using there? Oh, let's blow that up. That's building paper, for God's sakes. This is 2019. These are buildings built in Toronto in 2019. I assume they were approved because they're being occupied at this point in time. Who is taking responsibility? Where is the assembly? These don't even meet minimum building code, let alone the path towards 2032. So I like the idea that one day down the road, we're going to have to rate all our buildings on an energy usage, from really good to really bad. I know where these are going to be. And this is brand new stock being built today that are supposed to be here for the next 50 to 60, 100 years. If you look here, some of that exterior sheathing is already starting to degrade, and this is brand new construction. So, taking responsibility. Someone has to take responsibility. Someone has to take responsibility for the quality assurance. So an air barrier, and we're going to go through this again because it's really important. It must be continuous. It has to be supported. It's got to be durable. It has to transfer loads, right? We're going to have loads, wind loads, air pressure loads from both outside and inside. Creep, it's just gravity. Some of that stuff we saw was already starting to flop over. Well, it's not resisting much creep there. And of course, buildings move. Materials must be flexible. And that's really important because we're going to see it at the end. Certain air barrier materials, great, not flexible. We have to account for that. Flexibility, really important. So this is supposed to be a demo. I think it's important that we understand that anyone can put up materials. Okay. But it's that labor involved, it's that pride of workmanship, it's that craftsmanship that's important. Energy efficiency comes from not just the materials, but it's the assembly of those materials as well. Self-adhered membranes tend to be the superior product on the market. We have to be honest. There's mechanically fastened, there's self-adhered. Why do self-adhered work so well? Because we're not penetrating the membrane with a mechanical fastener. Every little penetration, every staple, every screw, every nail, in order for it to be considered continuous, must be sealed somehow. Somehow or other, you're going to have to patch that. The nice thing about a self-adhered system is that you don't have to patch. It's self-adhered. So there's a number of ways. I don't want to, this is really not how to install air barriers. It's the reasons behind we have to install it properly. Okay, I'm sure we've all seen air barriers, self-adhered membrane installed. There are 4 major components to it. We want to prime, so as we see here, we're going to prime. You can use a number of different ways to prime it. You can just roll it on, let it dry. You're going to take your material. There's a number of different products that you can use. So it's funny, we say peel. Yeah, it's really important. You got to peel the back so that you can stick it on. Have we seen it? Yes, we have, where they leave the backing on and it's flapping there. Okay, so I know it sounds silly, but it's important. Question.
Air barrier and vapor barrier, what's the difference?
We're going to get to that. So the question is air barrier and vapor barrier, and we're going to get to that. The next thing we have to do, these are what we call pressure-sensitive materials. They're designed with an adhesive. In order to get that adhesive to work, you have to apply pressure. There are many tools on the market. They're not expensive. It's part of the tool belt. It's part of the toolbox. You need these in order for the system to work. Weighted rollers work really well. It's an old cliche. Works better than the palm of the hand. Okay? It's not expensive, works really well, less fatigue on the installer, you get a better job, you get a faster job. Patience. Self-adhered, it has an adhesive quality. The adhesive is going to be much stronger, the bond, 24 to 48 hours down the road than initially as it's being put on today. So patience is a little bit that we have to have. So those are the 4 P's. Okay, there's something else at the end. It's an S. We can't forget that little S. You've got to seal it. Okay, so every air barrier membrane, especially if it's sheet applied, there's going to be ruptures, there's going to be holes, there's going to be defects. Sealants are really important because continuity, really important. There's a whole bunch of different compatible sealants available. So every little hole that you make through the membrane, you got to seal it. Okay, highly important. We have to take ownership. Someone has to take ownership. So that hole was designed for a specific pipe size. Someone decided to put a smaller pipe size. Someone has to take ownership to seal up that hole. There's a number of ways now that we want to seal because the massive size of that hole. Imagine how much air energy is going to want to transfer through there. There's always a right way and a wrong way. There's a right way to put on the air barrier membrane, there's a right way to fix it, and there's a wrong way. So we can get really complex to seal it properly for the life of the building, for the life of that membrane. This is just one option. There's other liquid applied products, there's other sealants that you can use as well. The key is to read the specification, read the technical data sheet, talk to your material supplier, and they will lead you down the right path. Okay, there's a lot of very smart people out there, technical people who can help you make sure that that membrane is continuous and working properly. I'm sure we've all seen a version of this down the road. I'm going to emphasize this. Really important. This is moisture and air transport over one heating season in Canada. So we make one little defect. This was a test, and research has been done to this for many, many years in Canada, the United States, Europe. This is not new. We have to emphasize this. One little defect. It actually accounts for 0.004% of the total wall area. In one heating season, you will have over 2,600 cubic meters of air that will be transported through that one little hole, that one little defect. And imagine the potential, the hundreds, the thousands of holes. How much air can pass through our structure, thinking that we have a membrane, but it's full of holes. Well, okay, that's just the air, but what's it carrying? It's also carrying moisture. We have the potential of depositing 30 liters of moisture within our wall assemblies, let alone all the heat energy that's going to escape as well, that the air is going to travel along with it. So again, little defects account for a tremendous amount of heat loss, air infiltration, and the potential of moisture deposit. Now that moisture comes in a variety of ways. Right now we're looking here, this is potential of vapor. What happens to vapor when it enters into our wall that doesn't have enough insulation on the exterior? Our dew point is somewhere within our wall assembly. We know the potential for condensation is really high, right? Condensation, warm, moist air hits a cold surface, turns into water. So that's danger. danger from a health standpoint as well as a structural. Dew point, I like dew point analysis. That's a shot. That's a snapshot in time. Hygrothermal analysis gives you a better view over 1 calendar year. So we did hygrothermal analysis for a structure in Toronto. We call it non-compliant. It's funny because it was non-compliant to the NECB 2015, but it was compliant to SB 12 in Ontario. So codes sometimes contradict each other. That's fine. This is still a non-compliant to NECB 2015. And we found that over a 7-month period, this wall, built in Toronto, Zone 5, Climate Zone 5, had 7 months of potential wetting. What we like to do, we say there's a wetting season and there's a drying season for our walls. We hope the drying season is equivalent or a little bit more, so that our walls have the ability to dry themselves if we deposit all this moisture. Well, the problem is, in this scenario, the wetting season is much longer than the drying season. So we see that walls have this tremendous ability to have water deposited within them. That leads to a number of issues. Two of the major ones, of course, mold and mildew, and that affects the health and safety of the people who inhabit it. It also leads to corrosion. Structurally, our buildings may want to fall apart prematurely. Imagine the cost of going in and repairing that. Sometimes, and numerous examples where the mold is so bad, the building cannot be saved. Okay, and the health effects are tremendous. Not only in the very young, but in the older population as well. We're seeing that mold and mildew really, really affect the very young and the old. The people in between, you may not feel it today, but you will feel it down the road. So indoor air quality, typically we see in some, I hate to say most, but there are many buildings where the indoor air quality is worse inside than outside. And we tend to live in a cold climate. We spend a lot of time indoors. The other effect, air leakage. You should always seal from the exterior. Okay, as we say, the interior air barrier detailing, that's a thing of the past. Okay, that's old news. That's old school. We want to seal from the exterior. We can reference numerous studies, again, within Canada, south of the border, Europe, numerous studies. We know that without a continuous air barrier on the exterior, all that nice fibrous insulation that we've put within our wall assembly, if we allow all that warm air to be washed out, we call it wind washing, you can reduce the performance of that insulation by up to 40%. Okay, detailed, right here in the NIST study, very easy to find. That's their conclusion. So, in other words, air barriers from the exterior really help to the insulation that's within our wall cavity to perform optimally. Insulation works by trapping air, warm, dead air. So we don't want it to wash out, to have this cycle of air moving through our insulation, washing out all that heat energy. Well, how does it get heat energy back? Because we have to transfer it. Many different types of products that you could use as air barriers. There's heat welding, there's liquid applied, there's factory laminated, there's self-adhered. All the way through here, you will notice that it's, again, not one individual product, but the key here is that there's minimal or few fasteners required to put these in place. Therefore, we're not rupturing the air barrier in as many spots. Insulation could also be used as an air barrier. The two most common types, spray polyurethane foam and rigid board insulation. So the interesting thing is that you do need a transition membrane for both of these. Again, one product cannot do everything. Spray foam, where do you put that transition membrane or that other ancillary product? You put it behind on the structure. and then you put on your spray foam. So it's on the structure, all your transition membrane. For your rigid board stock, you put it on the face. Different type of application, different products, you're going to detail it differently. They still work the same though. You still have the same outcome, the same results. It's all in the detailing, it's all in the workmanship. There's another really important part. So we've been talking about energy and movement of air. There's this other thing that we don't like to come into our building that's called water. We really try to do everything we can to keep it out. So what we do is one of the major sources of water infiltration is our windows and doors. It's those openings. Well, we have products designed to make sure that any water that enters into that opening is diverted back out. We call that flashings. We use it for windows, we use it for doors, we use it at numerous places. The point here is that any water that gets into this opening should find its way out onto the face of our water barrier, which is our weather barrier or air barrier, down the wall and then out the wall. Everything should be designed to exit our building. Because this is what could happen. We don't want this to happen. And we see this happening a lot. And where is this happening? At the bottom of a window. Again, there's a right way and there's a wrong way. When it comes to creating a flashing and installing the flashing, there's a right way and there's a wrong way. The wrong way is just slapping something on and hoping that no one will know. We see that a lot. I see it a lot. I tend to look for these things. So I stop at a site and I go, first of all, is there flashings? And second, are they installed properly? And 3 out of 4 times I can say no. I love it when I see a properly installed flashing. There's a number of steps. The key is that it's all in the workmanship. And there are courses, there's ways, there's detail. It's not rocket science. It's easy to do. There's people who can help. The key is whether it's a liquid applied, whether it's a sheet applied, we just have to follow the steps and follow the instructions. And especially at these corners, reinforcement is critical because that's where it's going to want to rupture. There's movement happening there and we want to make sure that it maintains itself. And then we want to make sure we use the right product. There's permeable products and there's impermeable products. There's products that are air and vapor barrier, which are also known as waterproofing, and then there's just air barrier products. Air barrier products that are vapor permeable are not waterproofing. Do not use them as flashing. Wrong product. They will leak. I guarantee you. You want to use a product that's waterproofing. An air and vapor barrier product typically is a waterproofing product. There's many out there. There's some that are various colors. Ours happens to be white and blue. There's one that's blue and white. Take your pick. We'd like you to choose this one. But the point is that flashing, do not use vapor permeable products. They must be impermeable. They must be waterproofing products. So we want to waterproof the opening and we want to flash it to the face of our air barrier or our water barrier or weather barrier, whatever you want to call it. So there's a right way and there's a wrong way. Again, the use of an air barrier and continuous insulation, they must work together. Just like air barriers, continuous insulation must be continuous. If there's a rupture, if there's a defect, someone has to take ownership. There's a number of things. The key here is in our Better Built Guide, Build Better Guide. We will detail all the different types of wall assemblies, their U value, their effective R value. It's a great little document to have. The key here is insulation must be continuous in order for it to be effective. And the other thing we have to consider, heat transfers from inside out. How do we reduce we want to use clips. The smaller the attachment, the less conductivity that there's going to be. We want to use less conductive materials, for example, for all our clips and fasteners, such as stainless steel as opposed to zinc metal. Again, you will find all these charts detailed to help you design your wall assembly. The various walls, we call it exterior insulated walls, or the industry term, perfect wall. That's where all the insulation is to the exterior. Now your membrane is both an air barrier, vapor barrier, and water barrier. Vapor barrier is always on the warm side of the insulation. When we separate the insulation, and now the bulk of the R value is within the cavity, the vapor barrier and the air barrier are now separated. Your air barrier goes on the exterior, your vapor barrier now goes on the inside face of our wall assembly behind your interior finishing. Always on the warm side. In summary, I'm going to say this again. I can't say it enough. That they must work together. Air barriers and insulation must work together. Thank you for your time. Please come visit us at booth 1102 and ask for your copy of this tremendous guide. And if we don't have it available, we will direct you to the website. And if you have any questions, thank you very much.